right, we can all go on the search for a package interface and look for that. So you just type in solar analysis for Dynamo right here at Dy2. Just go ahead and download that, and that will just install immediately. So Dynamo has this tool for running solar analysis in Dynamo, and then you have that data, and you can use it to drive geometry that you eventually author or edit in Revit. But then Revit and Form as well have Insight 360, which also runs solar analysis, and they don't talk to each other at all, unfortunately. So there's a bit of redundancy there that I'm not super happy with. So I think that's a bit of a critique of where the software lies at the moment, because if I have computationally savvy designers who are starting things in Dynamo, but then I also have what I would call a typical Revit user who might just want to be running that analysis in Revit, we should be able to exchange that data in a way that can be recognized both as generic data and kind of in a structured element of the Revit API, but that is not a thing yet, unfortunately.
Right. Are the
yeah.
results comparable at all? Do you know?
Yeah, I mean the numbers are pretty much the same. I would err on the side of Insight, which is a little bit more sophisticated. But the problem is it's just like a raw data set of numbers. They're not associated with the element in the way that a Revit object would be, because it kind of makes and we'll talk about that, like a Revit analysis object over top of the geometry. So in an ideal world, you'd have both of those things, and you could kind of exchange them back and forth, and that could be automatically annotated as like a Revit analysis element, or it could just be a set of dumb numbers that you're using to drive something in Dynamo. So the first exercise that I typically do, I'm going to switch over, I think this one can handle automatic, is just talking about how do I relate a collection of geometry to a collection of analysis in the form of number, and use that to differentiate that collection. So just a really generic example that has nothing to do with building performance or anything really. So this is the coloring with values, the very first Dynamo graph, and some of these graphs have like a start and a complete that just shows the various stages of them. And also just showing a few kind of Dynamo things along the way. So this is a function contained in a code block. So this is a dual code block strategy. I don't know if you're familiar with this, but it's kind of cool. Where you can use design script in two code blocks. So you use one code block to define a new function. So in this case, I'm saying that I want to do something that maybe like vanilla Dynamo nodes don't do. In this case, it's a 3D array of spheres or any geometry really. And then I'm going to call that new method that I just defined on the fly in a second code block, and it will just inherit that. And then all I have to do is provide those inputs, and I can call them whatever I want to. Zach Crom has pointed out that I could have just done a 3D point array and then hosted a sphere to that 3D point array, so that's super embarrassing. I have no credibility from the start, from the first definition. I'm up here design scripting like a noob.
That's called programming.
But that's all right. I still have a lot to learn. So the idea here is, all right, I have a set of geometry. I want to differentiate that geometry. So what's different about the spheres? They're all in a different location. And then I want to do some kind of false color analysis or data visualization of how different those locations are. So in order to color each object based on its location, I need one numerical value per sphere. So if you open the finished one in the data set, this is also a way for me to just avoid demoing, just a predate everything. And then we run this graph, you get some colored spheres. And the way this works is we have to get one number per object. That's how we're going to define this. So the way I can get one number per object is I can actually find the center of each sphere, and I can break that down into its x, y, z coordinates. That's still 3 numbers, so by summing the x, y, and z coordinates, I would get a different value per object. And you can see that if I zoom in. Here, this node right here, I've taken that function box array, which has done that kind of 3D array of those spheres. I've flattened that into a single list because I don't need a data structure anymore, so if I don't need it, I'd get rid of it because it makes life easier. And then I've used another code block out of that flattened list And I'm defining a couple things in that code block dynamically. I'm saying the center, which is a value I'm just declaring on the fly, is the centroid of spheres. So centroid is a design script method. It's just available out of the box. And then the values that I'm creating are simply the sum of the centers x, y, and z coordinate using the methods x, y, and z. And anytime I've used design script or Python, I've actually put the text in the handout too, so if that's easier to refer to after the fact rather than opening these definitions. So that establishes a value. So we now have a list of geometry, we have a corresponding list of values. And eventually those will be things that have to do with environmental analysis, like a radiation value. But right now it's just a positional value, an arbitrary value really. So the next thing we want to do is define a color range. So if you just right click and search color range, that is a node that should be available to you. It takes 3 inputs, whatever the colors are that you want. It takes the indices of where those colors occur within the range. And then it takes the values that you're passing through that range, which is basically a way of taking a series of numbers and remapping them to colors. Do we have any Grasshopper users in here? So at first I hated this because it didn't have that dynamic UI that you have in the kind of Grasshopper gradient component. But I actually think that it's better when every single input can be controlled by a number or numerical value as an input and you don't have any fancy UI. That allows you to actually kind of have greater parametric control in the long run because while you could perhaps script a kind of custom UI thing moving around, that becomes a lot more difficult. So I kind of came to like this, but it's a bit of a effort to set up because the first thing we need to do is we need to create a list of colors. There's actually another package for Dynamo that's I think just called Color UI or something like that. I think that was Adam Schiefner, I forget. But it's got like a more kind of dynamic UI for picking a color. So out of the box with Dynamo, you just have to set RGB values. So you're just saying like, what's my false color analysis gradient? So usually like blue is like the lowest intensity of something and red is the highest intensity of something. So the position, the kind of coordinate position of the sphere, I'm just saying like it's more intense as it moves farther away from the origin. So I just define the colors blue, yellow, and red using the number 255, but then selectively plugging that into the RGB inputs to make the colors blue, yellow, and red. So it's kind of a lot of blocks to make a list of colors, but then I use a list create node, and that's how we can combine those things into a single list. So if I drop that down, it recognizes those colors there. So that's the list of colors that feeds into the color range, and that's going to basically define what's occurring in that particular UI element. But then the indices are saying, like, where do those colors occur? I just need to stand still. So typically, if I'm supplying 3 colors, it's like, well, I want the first color at the left, the last color at the right, and the middle color in the middle. But to specifically indicate that, you need to provide a normalized range. So it's saying, between the values of 0 and 1, where do you want these colors to occur? So I'm saying blue is occurring at 0, yellow is occurring at 0.5, and red is occurring at 1. So imagine what a huge pain in the ass it would be to then like add a 4th color and be like, oh, well, now it's different. Now it's 0, 0.3 repeating, etc. So it would be better to create some kind of parametric relationship that could basically create that those index values for you on the fly by counting the length of the list of colors you provide. So that's what this code block is doing right here, generating the indices based on the color count. So in this case, I'm saying the steps, and the steps being like the amount of times I divide the range between 0 and 1 is just going to be the list.count of the input colors. So list.count just being the method that says how many things do you have in the list. I have 3 things, and then I can use this kind of little range syntax here in design script to say start at 0, end at 1, and then divide that into 3 steps. So then the numbers I get, if I hover over here, actually, there they are, 0, 0.5, and 1. So if I were to add a 4th color, so I'll just copy and paste. Add another object to that list create. So it's, like I said, it's kind of a little bit of, it's like a lot of components to have to do for that, but once it's set up right, it works quite well. And you're typically like, if you're doing stuff like typical solar or daylighting analysis, you're typically working with the same color ranges all the time anyway, so you can just wrap that thing up into a little custom node and use it whenever you want. So that's the general premise here. It's like when you're doing this type of analysis, you have a series of objects, you have analytical values associated with those objects, and then you can kind of visualize them with some of the color tools available in Dy2. So, moving on to the next step is using the actual solar analysis tool to drive this analysis. So instead of doing some kind of arbitrary analysis like sphere position, I'm actually going to say I want those solar radiation values, also referred to as insolation values. So here I am again doing kind of the same thing that I did before with this double code block method. In this case, I'm making a sinusoidal surface. I just wanted to make some kind of arbitrary geometry or arbitrary shape that had a lot of different angles of incidence relative to the sun, so that we can kind of see some different colors. It would be prettier that way. So I'm just defining a quick function called myWave. It's a one way of many to create a sine wave or control the editing of a sine wave. And then I call that function down here, and it takes a few inputs and just makes something weird. So I then pass that into a code block. Sometimes for clarity, I pass an object into a code block, and the code block does nothing. It just gives me a chance to kind of say, here's where that thing lives. And then here's a series of things through here that we don't need to get into too much, but basically this is just some geometric manipulation. So I'm using Dy2 to take one sine wave, because I want an alternating sine wave. This is that like egg crate that you get on those like really comfy mattresses. So you take one sine wave, and then you copy it, and then you mirror it about its own center, and then you copy both of those things. But then you have one list of sine waves that are oriented in the proper way. You have a second list of sine waves that are mirrored. So you have to actually merge those things in together in an alternating fashion. So if I had two stacks of cards and I were combining them, kind of like from pile A, from pile B, from pile A, from pile B. In grasshopper parlance, that's called a weave. So to weave a list, there are actually a couple ways to do this. Some people have done some fairly clever ways, but again, as far as I know, there isn't like kind of a straight up, like out of the box way to weave two lists. But the way I typically use is a list.combine. The kind of combination method there is a list create, which essentially creates an alternating sequence. And frankly, I don't totally understand how that works, but it's one of those things where you just try it a few times and then you keep using it. And then pass those two lists in, it kind of weaves them together. And then I do need to flatten those lists when it's done, because I'll get a series of sublists, each with two lofts, or with two loft curves, and a loft just wants to have a single list of curves. So again, none of this really having to do with analysis, except for trying to create different angles of incidence, but just a few ways of creating some weird shapes in Dy2. So then the next step, which is the finished version of this, applies solar analysis. And the solar analysis is just one kind of big node. So again, if you right click, after you've installed that package, and just search solar analysis, stupid Dy2 search, right, try analyze. Yep, all right, just type analyze. And you can see it's got a number of inputs here. So, and this is stuff that, this is the stuff you need to run solar analysis. And solar analysis doesn't require any kind of like underlying environmental engine, because it's basically just math and solar angles. So it does need to, however, like pull information from a weather file. If you're using something like Ladybug, you're typically actually going out, getting the weather file, linking to the weather file, and bringing that data into Dy2. So one of the kind of nice shortcutty things about solar analysis in Dy2 is that there's just a few like pre-made components that kind of dynamically do that for you. So in this sample definition, first I'm going to define the weather. And this can all be found once you've loaded that package in the analyze drawer. in the library under solar analysis, and then under weather, actually quite a few ways to define the weather here. So I chose to do it by latitude and longitude. I Googled where Scottsdale was, typed those numbers in. Hopefully I got them in the right order. That probably makes a difference. And then plug them into the weather input. The analysis surfaces, so it can take one surface, which is what we're doing here, and then just differentiating like the amount of radiation at different points on that surface. Or, as I'll show you in another exercise, it can take a series of elements like curtain panels and analyze each one of those separately. So this surface by loft, which was the last component in the first definition, the resulting surface that we lofted from those sine waves, then gets plugged into the solar analysis .analyze under the analysis surface. So we're saying that's what we want to analyze. And then typically when you're doing this with like buildings, you have shading. You might be doing something like a facade study that actually has shading elements on the facade, in which case those would be the shading elements, and or urban context or site context that might be casting shadows. And I believe this is taking care of self-shading as well, just inherently in the analysis surfaces. So one little kind of weird thing about the way this component works is that if you hover over shading surfaces, you get a little tooltip there. If no shading is desired, you have to input an empty list, which is just a dynamo node to specify nothing. Something poetic about that. So list.empty. And then, so in this case, I don't have any shading. And then you need to put in a time study. So again, you're setting some kind of analysis period for when you want this study to occur. So keeping it topical here. When does RTC start? And then doing a time study from sunrise to sunset. So the time study stuff is also in here. I think it's under analysis, yes. Solar analysis, time study. And you have a couple options. Still is just in the present moment. From start time to end time is just like a full span of time. But sunrise to sunset is typically what I would use. And if you wanted to do some kind of full, like cumulative annual study, then you could just set it from January 1st to December 31st. And then it has the information from the localized kind of weather file in Scottsdale as to when sunrise and sunset occur, so that it's just getting the radiation when the sun is actually out, which makes sense. And then the last thing you're providing is the analysis grid spacing. Now, this is just some weird form, so it doesn't really have units, but whatever it was, I decided that 2 was a good number. So for a building, this should be an actual dimension that makes sense. So if I have something super curvilinear, then I probably want to analyze it with a denser analysis grid. So I'm going to have a smaller number, so I get more data points. And then I kind of decide how I want to use that. Am I summing everything up? Am I finding a worst case? Am I finding an average? It depends on what you're doing. I do a lot of stuff just based on worst case solar radiation per element. That's maybe not always appropriate. Maybe it's never appropriate, who knows? But the idea here being that, again, resolution is based on geometry. So you'll see later that if I run the same analysis and keep that spacing of 2 on a bunch of curtain panels that are planar, then I have a lot of redundant information. I don't necessarily only want to have one data point because you can get singularities and weird values that could throw things off. But by and large, with like a planar element, every single one of those numbers is going to be the same. So you have to think about what you're doing. I think mostly with architectural analysis, you're dealing with planar stuff, but not always. Curve stuff sometimes. And then running that visualization, and this is the same exact set of nodes that we dealt with before, with one critical change, which is if you look up here, this display node. So there's display by object, and there's display by surface color. So in the prior example, we were saying there's one color per object in the scene. Here we're saying I actually have a bunch of sample points coming off of this surface, and I want to kind of create that visualization accordingly. So if I run that, we should get like a rainbow bright sinusoidal surface here. Yeah. And then that should roughly make sense. So one thing that was kind of throwing me off, this is like the first time I went to Australia and I was like running Ladybug on a project and I was like, why is everything backward? So where you are on the planet determines how the sun hits you. So I realized that we're fairly far south in Scottsdale, and at this time of year, the sun is like a lot more directly overhead than what I'm used to, like running analysis in New York and stuff like that. So you're getting like a ton of stuff kind of on the east and west, and not as much on the south face as I would have kind of expected. And then you can see that kind of blue coloration on the north face where it's not getting a lot of heat or energy up there. So, I mean, one thing that you could extend this workflow, and I did a similar workshop to this at AU, where the idea was this was a base surface for like a train shed or something. So then we could discretize this surface or divide it up into subsurface patches and then drive the population of like Revit panel elements on that with those different data subsets. But in this case, just using this as an example to show you coloring something by multiple values on a single object rather than one value per object. All right, so now let's make some architecture. So the next one is solar-driven design here. I think I left some mistakes in here intentionally. And this one will require the companion Revit file. So I've got like a little portion of, this is actually a project I'm working on right now, and I just like chopped off part of it so that we could run analysis on something that was twisting a little bit. Which also means that there's probably some embarrassing like data mess inside of this file, so don't judge me. So yeah, go ahead and open that Revit file. You should open the one that says 1.3 exterior wall, as opposed to exterior wall final. Exterior wall final has already been transformed by the solar analysis values. So if you want to see that change, then start with this one. And here we're going to interact with the Revit model, because that's really the main reason that we're using. I know there's like Dynamo Studio and a lot of other uses for Dynamo out there, but like I'm always using Dynamo as a way to talk to Revit. And in this case, the first thing I want to say is I want to ask a question to Revit, which is like, give me all of your glass faces. In this case, there are these window families, which you can explore on your own if you're so inclined. They have these shading hoods over them, this kind of trim around the frame, and the entire frame can extend, and then there are instance parameters for each corner of that, so if you wanted like one edge or the top to extend more than the rest of the corners, you could. So right now they're all consistent, they're all the same dimension, but the idea is I want to run solar analysis on every curtain panel, so each window family contains one curtain panel, one piece of glass. Collect that data, and then remap that data to some kind of value that will then drive that shading element. The basic premise being that solar radiation, while not the kind of definitive indication of things like thermal comfort, cost savings, necessary shading and things like that for internal daylighting, it's a pretty good like early benchmark. So we can create this kind of one-to-one proportional relationship to how much solar energy is hitting this glazing and how far our shading is projected. So it kind of gets us in the right ballpark, and then we can run some kind of companion analyses to refine that design, and then work with our consultants to kind of push that even further. So the getting of the glass faces, this is actually way overcomplicated. Again, I'm just like copy and pasting stuff out of other definitions. What this script is saying is I want to get all the elements of a certain category on certain levels, but in this case I'm actually just pulling it from all levels, so you could just get all elements of the category curtain panels and it would probably work the same. I don't want to mess with it and break it or something. If you're curious, you can go in there and have a peek around. Can you make this larger? It's tiny. And it's just like a filter, like a collection and filter method there. If anyone went to there was like a getting started with API class yesterday, kind of went over those methods. It's a good place to get started. I'm not very good at the API at all. It's kind of where I started. So that's like filtering out a few things, but again, basically I'm just saying get all curtain panel elements. And you can see that like if I just put a watch node on here. So instead of seeing some kind of description of geometry objects, I should see actual Revit elements. One indication of that is there's a GUID following the description, but you should also see some kind of like recognizable category in the description as well. And then there's the process of, because that's Revit stuff, so once Revit stuff comes into Dynamo, it has to be turned into Dynamo stuff. So then that's the element.geometry component that's following it. So I just ran what I had in here. So if we look at it, that's all of our pieces of glazing. So I've converted those curved panels, but Revit's a solid modeler, right? So there are a few extra steps required here, including a hilarious sequence of list maps. I tried to cleverly list lace it or something, but I couldn't figure it out. So I have the Revit element, and then I got the Revit geometry, which is a solid, but then I needed the faces, so I got the faces with topology.faces. And eventually I need to convert those to surfaces, but for the purposes of this analysis, I don't need a solid for it, I just need one surface per glass. So then I had to extract a single face out of each one. So the problem here, for those of you nerds interested in how these data structures work, I'm not particularly interested myself, but I'm willing to talk to you about it. Is we've got you can see all of these nested lists, and that's totally my fault again for using this dumb script when I didn't need to, because it had actually kind of pre-divided up things per level. There are a lot of times when I need that. This is actually a derivative file from doing something we have in NYC called Light and Air, where I needed to pull Revit glazing and Revit rooms per level, and then federate all that data in Grasshopper, because I was doing stuff that was tricky with geometry and data, which Grasshopper's better at still. But still need all of them, still need to hook everything up together. Maybe I'm just not good at that enough. So you have all these lists, so you have to drill down into them. So Grasshopper works from the innermost list. So you can see here I have a list of a list of a list of a list that contains 6 faces. So with Grasshopper data trees, if I said, give me the first item in a list, it would assume that I was operating on the innermost one, and it would give me that first face, and I'd be happy to be on my way. And by the way, this data stuff is going to be changing, or it has changed in Dynamo. It's going to be a lot more agile. But there are good reasons to go both ways, it doesn't matter. So to dial that in Dynamo, if I say I want the first item in the list, it's going to say, oh, you're going to get the first list of lists. It's going to go all the way to the left and just give you whatever the first list is there. That's not what I want at all. So I need to drill down in there. So the function I'm using is get item at index. So get item at index just says, give me an item in a particular spot in this list. I didn't do anything clever with how I was selecting these spaces. If I was really clever about it, I'd probably put a point in the middle of the tower and say which face is farthest away from that point, and that's the exterior face, and I'd grab that. But I knew that all the data was organized in the same way, so I did something that's kind of bad, and I just said, just give me the second one, which is index 1. So God forbid the geometry ever changes, this probably won't work anymore. So then I had to do a list.map, so that applies that function one level in. So it maps that function of getting the second object to the internal list, but I wasn't in deep enough, so I had to incept further with the second list map, and oh my god, a third list.map. But it's my own fault, again, for how I structured the data in the first place, so that's the question I should be asking here. So what I'm doing here, this is weird. This is really weird, because what you're doing is you're mapping the function kind of against itself, or against nothing. You can see I'm not actually mapping anything. I just keep feeding functions into list.map. So I'm creating a super list.map function. It's basically every time you add one, you're kind of embedding the instructions in that function to go one level deeper, one level deeper, one level deeper. Oh yeah.
You don't even want to see that and do that.
So that's kind of how you can move. And there's I'm sure there are better ways to dial into different levels. I'm sure Zach is upset right now that I'm teaching Dynamo like this, but
All good.
you don't give me enough attention, Zach. I'm acting out. So So then, once I have that function, which is a specialized function that's intelligent enough to go like X levels deep into my data, then I'm applying the faces to that. So then I actually give it a piece of data. So now it's ready to go in, and then like I flatten the whole thing because I'm sick of data structures at this point. And then I have a list of those faces. So that's all the nonsense that's happening in there, but I mean, you have to come to terms with that at some point in Dy2. Those lists of faces are then being analyzed. And then if we look, so again, even though I had flattened those surfaces, oh, had I? That doesn't look flat. Oh wait, that's not the surfaces, sorry. So I flattened those surfaces, but because I'm giving it a bunch of different objects to analyze on, it's basically going to make an analysis grid on each object, which means I'm going to get a bunch of analysis data points per piece of glass, which means that I can't just take these peak values. So you have cumulative average peak, and then the actual calculation points themselves. So I like to do worst case scenario stuff. So then I just take the peak values there. But it's going to be too much information, so let's look at that and let's fix that, because that's not ready to go. So again, I'll put a watch note on it so I can see what's going on. And you can see I have a list of a list of a list. So I know that one of these lists just seems to be empty. It seems to have no purpose. I'm not sure why it's there. I don't understand what's going on. So I'm just going to remove it. And the way I'll remove it is to flatten by a single level. So I'll take that list. So normally when you flatten a list, it just ignores all structure and just puts all of your objects into one list. But if you flatten by one level, it will just kind of take one nested level out of there. So far as I know, you can't use negative numbers. You can only flatten with positive integers, and that will cause another fun challenge for us. So if I plug this in and run it, is that right? I can see, here's how I should do this. If I want to know what's going on, is I go back to my surfaces. Say, I'm going to watch my surfaces, because I should see how many windows I have. That should be the first thing I'm aware of. So I have 378 windows. I should have a corresponding set of lists, that is, I should have 378 lists of values as well, so if I scroll down. So I have 2,330 lists. Whoops, that doesn't seem right. And the problem here is I flattened the list the wrong way. And I can't put -1 in to flatten it the other way. So remember, Dynamo works from the inside out, so it's actually flattening the list from the inside